Okay, so welcome back. So in this course, like we have so far discussed the basic idea about diffusion models, including some the DDPM and the DDIM, and also we had the assignments in terms of how to implement these things with some kind of the simple the toy setup with some kind of 2D points and very small set of images. And from today, we are going to switch the gear a little bit in terms of like discussing more practical ideas in terms of like how we can really implement the diffusion models for the very large scale data set, and how we can also apply these like degenerate models not only for the some typical the generation the tasks, but for some special cases like the conditional generation, personalization, and also many other cases. So the topics that we are going to discuss for today are more like the practical the ideas, more about some kind of implementation, and some of them may not be based on any kind of the theory. So you can be relaxed and just like see what are some kind of the basic ideas there. And we're gonna also go quickly through the, like a whole bunch of the ideas in terms of like how we can make some kind of the conditional generation, do some kind of conditional generation, personalization, and many other things. And also what we are going to discuss in this session for the assignment 3 is more about basically how we can play with some kind of the pre-trained diffusion model, not the one that you implement in the previous assignments, but some kind of the well-known the pre-trained model like the stable diffusion, and how we can use that for so many of the applications. So like one big, the two big questions that we are going to discuss for today is basically the first one is that how we can use some kind of the extra information in the generation. So for many kind of the types of the data, for example, like the images, there can be some kind of like accompanying some sort of the extra information. For example, we might have some kind of the class labels for the images, or there can be some kind of the text descriptions for the images as well. So here, like the one key question is that how we can like further utilize this kind of the extra information coming with this kind of the images that we have in terms of like improving the quality in the generation, and how we can also turn the diffusion model into the conditional generation is the first question. And the second question is that now we are also going to see some kind of the pre-trained diffusion model, which is trained with some literally like billions of images, and how we can basically utilize this kind of the pre-trained models in terms of some other the tasks by fine-tuning the given the diffusion models. So we can also very briefly discuss these kind of the ideas for today. So these are the topics that we are going to discuss for today. And if we have some also the additional time, we can also discuss some more like the zero-shot the applications as well. So last time we briefly discussed the idea of the Classifier-free guidance, but today we are also going to get into some more details for that while starting with the classifier guidance first. So the basic idea about the classifier guidance is that, as I mentioned in the previous slide, given that we are having some kind of extra information, so especially for the images, we can assume that for many of some images, the data, there can be some kind of the class label information, like these are the images of the airplane, like these are images of the dog. So when you have this kind of the class label the information, how we can use this information to improve the quality of the images. And for that, the basic idea is to basically utilize the classifier for the kind of images. So here, basically, the basic assumption is that we are basically having the pairs of the data, basically having a image and the class label, and there can be also image and some text description or some many other things. So in this case, like what we want to do is that we want to basically model the joint distribution of these kind of two items, images and also the labels, which can be represented into this form, basically having the pxt multiplied by the py conditioned by xt, right? So how we can model this kind of joint distribution? And for that, basically what we also have seen last time is that basically the epsilon, the noise that we are predicting using the neural network is basically related to the score function in this form, right? So basically we can have this kind of like formulation connecting the noise that we are predicting with the score here. So like what we are basically playing with here is basically like all about predicting the score in the basically diffusion process. So for now, let's simplify the notation this way in terms of that the epsilon t is basically connected to the gradient of the log the probability of the xt here. So in terms of like modeling the joint distribution of the xt and the y, what we just need to do is basically how we can basically get this core information piece, right? And given the formulation that we had in the previous slides, now we can decompose the score of like this, the joint distribution into this term. And which means that now we need to update this core, not just taking the epsilon here, but actually into this form, right? So you can see that given this core function, now we are having that this term as kind of our new score, which means that we need to basically have some kind of be able to calculate some kind of offset that is basically added to basically the noise that we are predicting using neural net. So basically here the idea is like the question is that how we can get this information. So if we can calculate the score for this specific conditional distribution, we can basically get some kind of the rectified noise with the kind of the joint distribution. So then, which means that we should be able to basically model this probability, like given the xt, what the label, the class of the xt. So what is such kind of the neural network that can predict the class label from the given the kind of the noise image here? So this is basically the classification network, right? So the role of basically the classification network is taking some kind of image as the input and then basically predicting the class label, which is for that specific the input, the image. So once we basically train the classifier, we can see that actually the classification network is basically modeling this specific the conditional distribution, given the xt, predicting the probability for each of the class label. Right. So which means that we just need to have the classification network that can provide the information like this specific probability. So we can think about like having another classification network, taking the noise data, the xt as the input, and then predicting the probability for each of the class labels, and then update the noise into the in this form. So it's just matter of basically computing the gradient of the classifier here. So this is like very simple the idea in terms of how we can model the joint the distribution in terms of having another neural network, which is the classifier here. And also, as we discussed last time, like we can do some kind of the enhancement of the condition in terms of that we are having this kind of some kind of parameter like the omega here, which is greater than the 1, in terms of like we are enforcing the condition more in terms of like the kind of the like guidance for the noise. So here the question might be what's the meaning of like having this like the weighted omega here, right? If we rewrite this formulation into this form, basically rewriting this formulation into the form of the noise again, that what we can see is that actually this turns out that we are basically calculating the score of like this joint distribution. So can you see like how we are basically deriving this formulation at the end? So the meaning of like this is that actually we are sampling from this joint distribution, which is basically decomposed into this. But instead of like sampling from here, the joint distribution of like xt and y, now we are sampling from this specific distribution. So there is basically no any kind of like meaning of like having this distribution, but at least like what you can see is that we are basically amplifying some kind of the large probability from this conditional distribution. So which means that we really want to sample the xt, the image, which is really classified into this specific label. So how we can basically generate some kind of images that can be really basically classified into that specific label, not being confused into the other class labels. So basically by amplifying this conditional distribution, what we can get is that we can basically get some kind of the higher fidelity, basically meaning that we can really produce the images that really look like that specific class labels, but probably we might lose some kind of the diversity. So that's basically the meaning of that we are having that the weight, the function in this formulation, in terms of that now it turns out to sample from like this specific distribution. So this is kind of the same thing that we have seen in the CFG case in the last lecture, and we are also going to get back to this point again. So the kind of thing is that now, the advantage like having the classifier the guidance is that in this way we can actually improve the quality of the generation. But also the good thing is that now we can make some kind of the conditional generation. So given that when you have some kind of some labels for the images, like given like represented like as the y here, we can basically generate some of the images that can be classified into that specific label. So we are basically making some kind of the conditional generative model, which is taking the class label as the input. The downside is that this also requires to have another network, which is the classification network. And also it may not work that well when we have some tones of the labels. Like for example, like what if we have the 1,000 the class labels, or more than even the 1,000, like 10,000 and more than that. Then also the quality of the classification will not be that good. So that basically motivates to basically introduce another way to have some this kind of the conditional generative models. So this is basically the idea that we discussed last time, which is not to have another neural network, but using the same network both for the unconditional and the conditional cases. So here the idea is that we are basically somehow modifying the noise prediction neural network in terms of that we can take some kind of the extra input, which is the condition here. So that can be class label or some kind of the text description or the images or many other things. So we are going to also discuss some more details in terms of like how we can modify the noise prediction network to incorporate some kind of the extra condition. But here the thing is that we are making a single network both for the conditional and the unconditional case by basically introducing some kind of the null label. So the null label can be anything that you define. For example, if we have the class labels, like 0 can be null label, and some kind of the integers can be the labels for the the classes. So it's a matter of like how we define the null label. And feeding the null label here basically means that we are not providing any condition. So that's the unconditional case. And we also discussed the idea of like the condition enhancement as well. So as we basically had the parameter of the omega in the classifier the guidance case, we can also think about basically doing some kind of the extrapolation between these two by having this kind of the omega here in terms of basically modifying the noise as well, basically having the noise of the conditional case and the noise of the unconditional case. Okay. Then you might have some question about like why is this like extrapolation? The formulation doesn't look like the extrapolation, no? Can you guess like why this is basically extrapolation? So if it becomes like extrapolation, then the formulation should be like something formulation of the interpolation, right? Any guess like why this turns out to be extrapolation? So yeah, we can think about this. Actually, the easy way that we can see like how it basically becomes like extrapolation is basically changing the parameter in this way. So instead of like taking the omega here, if we introduce like lambda, which is basically the 1 plus the omega, then what we can see is that now it really becomes the form of the interpolation, right? Interpolating this, the conditional noise with the unconditional noise. So if the lambda was in the range from the 0 to 1, then this will be some kind of the interpolation, right? But now we are basically making this lambda to be 1 or greater than 1 because like omega is like 0 or greater than 0. So which means that now this form becomes the extrapolation between these two. So this can be also rewritten into the form that we are starting from the unconditional noise and basically, adding some kind of the difference between the conditional noise and the unconditional noise with some kind of the weight. Make sense? So in terms of that, we can see that actually this is indeed basically doing some kind of extrapolation between the two nodes. And also, what's the connection between this with the classifier guidance? So what we can also additionally see is that if we also like rewrite the same formulation, basically having this kind of like having this kind of the extra term kind of the difference between these two into the form of the noise again, then we get basically this kind of formulation. So I'd like to recommend you to check this out yourself after the lecture. Basically just like rewriting all the formulation. And from this, like what we can see is that if we basically multiply the py, the probability of the y to the lambda here, which is the constant, and apply the base, the rule here, then we can get into this form, which is exactly the same the probability distribution that we have seen in the classifier of the guidance case. So after like rewriting all the formulation, what we can see is that actually this becomes the same as basically sampling from this specific distribution, which is basically the same case that we are having the omega here. Actually, it does not omega, but basically lambda in our case. So what we can see is that even without like having the classification of the network, we are basically doing the same thing with the classifier, the guidance. So this is like why this basically idea is called the classifier-free guidance. Basically doing the same thing, but without having the classification of the network, but by basically having the noise prediction network that takes basically the condition as the extra input. So you can see that these two are basically exactly the same in terms of like sampling from the same distribution. And this is also the image that we have seen in the previous lecture in terms of like that, you know, as we increase the weight for the conditioning from the 0 to the 4 here, we can see that we are seeing some the images of the specific the dot here. So as you can see that we are losing some diversity, but generating the images that is really aligned to that specific the class of the images. So the assignment 2 is also basically it's about implementing this like classifier-free guidance, and I recommend you to basically play with the weight in terms of like what you get as kind of the final outputs. And there is basically the trade-off in terms of like basically the fidelity and the diversity. So as we increase the weight, we get some kind of the really good images that are basically really aligned to that specific condition, but we are also losing some diversity. So we can play with the weight in terms of like, you know, that we get the best results in terms of the diversity and the fidelity. So this is also the result that has been shown in this paper in terms of that, you know, if we use the classifier guidance, then we get this FID. And as we play with the weight in the classifier-free guidance, sometimes like we get the bad results when especially the W0. So W0 means that there is no guidance. It's typically the DDIM. But if we start to basically increase the W, then we can get some kind of best result, which is even better than the classifier guidance. So the good thing of like this idea is that you will see that actually this is really easy to implement. So that's why we are also adding this to the assignment 2. Just below basically having another sort of the encoder for the condition to be fed into the neural network. And also it's really versatile. So for the classifier, the guidance case, the input should be really kind of some class labels, because like we need to basically train the classification network. But here, the input condition can be really anything. It can be like text description, it can be images, or many other things. So in terms of that, we can easily incorporate many different types of the conditions. This is basically more the versatile the model than classifier the guidance. The only the downside is that basically in the generation the process, we need to predict the noise twice because we need to have the noise for the conditional case and the noise for the unconditional case. So that can be kind of the one downside. Any questions on this? So you will see that actually this is really practical the idea that you can see many diffusion models. Literally like most of the diffusion models that are released to the public are basically using this idea for some types of the condition. So most of the image models are actually taking some of the text description as the image as the input. So most diffusion models are basically the text to image the model that is called the T2I model. And this is the state-of-the-art the T2I model. Actually, there can be some more. We are seeing like new models almost like every day. So this is like one of the most famous the T2I model, which is Stable Diffusion version 3. You can see really nice quality of the images generated from all the texts. So here the text is very small, but the first one is basically detailed pen and ink drawing of a massive complex Aryan spaceship above a farm in the middle of the nowhere. So you can see that the output image is really capturing all the kind of the descriptions as given as the input. And also like having the text in the image was like one of the very challenging in case. So it's a photo wave bear wearing a suit and top hat in the river in the middle of the forest holding a sign that says, "I can bear it." And it usually basically take this text, "I can bear it," in the sign here. So very surprising. So for those kind of the very recent the T12 models, the classifier-free guidance is basically used as some kind of the basic component. So you will see that actually this is really, really basic technique for many of these diffusion models. Like another example, like the text-to-image generation. So these are also very like interesting images, unusual kind of images. So, and then some more images here. Yeah, and also you can see some kind of the variation as well. Like from even the same prompt, we are seeing some kind of the small variations in the outputs. So you see that actually the CFG, so the classifier-free guidance, like CFG is just a very common technique for the T12 models, and it can be also used for the many image-to-image degeneration as well. So this is like one example using the CFG for the like image conditioned image generation. So there are also lots of some kind of the models that are not using the CFG for the image conditioning, but the other ways. But this is like one example of using the CFG for the image-to-image model, which is taking not only the prompt here, but some kind of some input image here in terms of like making some of the changes of input image following the description. So like add the fireworks to the sky, to the Eiffel Tower here, and make this jacket out of the leather. So we are basically making these kind of changes. So for those kind of the conditional cases, like the CFG is also used. This is another like the famous example, which is basically generating the images of the object from different view. So when you have the image of the object and also some kind of description about the camera angle, by just taking these two information, the diffusion model is basically generating some kind of the image of the same object from different view. So for those cases, basically we also will need to basically take the input image and just collect the camera information as the input. And this extra information is basically fed into the neural network into the CFG idea. So those are also the examples of like using the CFG, and there are actually quite many. Not only for the image generation, but also the 3D generation. There are also kind of examples like using the CFG. And this is also kind of interesting example that we are basically generating the shapes of the two hands. And for those kind of cases, like we can generate like one hand conditioned by the other hand. And this might be also another example that we are now generating even the images from the audio input. I'm not sure whether it's hearing these sounds, but let me check. Let me share the sound. Can you hear the sound? Yes. So it's the sound of some kind of nature, then we are generating those kind of images. What do we expect to see from this sound? So images of the world. This is image from the world. So yeah, for those kind of the examples, like the applications, we can consider it to be CFG. So it's very common technique. So speaking to the CFG, also the interesting kind of the way to utilize this technique is to basically have the negative prompt. So these are also some of the examples, like making some images of the portrait of the Jimmy Acton. I don't know, like what this means, but making some kind of the monster images. And we want to enhance some factors in the generated images, not only the kind of things that has been described in the given the text prompt, but something else. For example, like I want to make this character to be more like the female, or I'd like to make this character to be more like the male. Then what we can do is that we can introduce some kind of the negative prompt in terms of basically reducing this factor from the generated images here. So this is like an example when we take the male as the negative prompt, making some more like female images. And also when we take the female as kind of negative prompt in terms of making some more like male images. So simply what we can do is that we can basically, instead of like using the null prompt in terms of like enhancing the given the prompt, we can replace this like null prompt into the another some kind of negative prompt. Having the positive prompt and the negative prompt in terms of basically enforcing more into the this case. So if you play with some kind of the pre-trained some kind of diffusion models, like what we typically do in terms of the prompt engineering, in the positive prompt, we can say like high quality, like the high resolution, like clear images, whatever some kind of some positive words. And the negative prompt, you can put something like the blurry images, like low quality, low resolution, whatever things that is basically including some kind of the negative meaning. So by basically playing with this kind of prompts, by doing some kind of the prompt engineering in this case, having basically both the positive and the negative prompts, we can get some kind of the more some kind of the better results in terms of that the basically following some kind of the some users kind of the kind of like basically some ideas there. So these are some very practical ideas in terms of making some kind of conditional generation. Do you have any questions on this? So what we are going to do in the assignment 3 is that you will basically need to play with some pre-trained diffusion models and see what happens when you put this kind of some kind of prompts into the pre-trained models. And for that, we're going to briefly discuss the idea of the latent diffusion. So the thing is that like when you see some kind of the pre-trained diffusion models, these are basically the cases which are basically trained with the literally billions of images. So these are really the cases that we are getting the old images, almost like old images in the internet, and using this information to train a single diffusion models. So here the question is that how can it really like scale up in terms of training diffusion models that can be trained with billions of images in a way that we can really produce like all the like imaginable, some possible images using the single model. Also, in terms of the resolution, now the images that you are generating in the assignment, the very low the resolution images, like 30 to 64, those kind of things. But if we want to generate some kind of the high resolution images like this, what sort of the diffusion model should we use? So there are basically the challenges in terms of like how we can scale up the training data set, and also how we can scale up the resolution of the images as well. And what happens is that if we start to train a diffusion model for this kind of the very large scale images and also with the very high resolution images, what will happen is that we will need to use tons of the GPUs. So now you are using a single GPU for your assignment, but for typically for training some kind of the very large scale diffusion model, we will need to basically have like single GPU and training for the hundreds of the days. We're either having the hundreds of the GPUs to be trained to train this model like in a few days. And not only for the training, but also for the generation. If we especially like play with the very high resolution images, it will take like days. So what is basically known from some previous some research papers is that if we want to generate some kind of the 50,000 images with some for some higher resolution cases, it will basically take like some days, like 5 days for that. So here the question is that how can we make some kind of the more efficient diffusion model that can more effectively handle some large-scale images and also higher resolution images? So the very basic idea that people are all using for many the public diffusion models is to basically utilize some kind of the image compression. So in terms of the compressing the images, the idea that we also discussed in the second lecture is to basically use a autoencoder. So what we are also going to do is that we are first going to basically compress the images into the much low resolution, low dimensional some kind of data. In terms of that, for example, if we have the 512 by the 512, the resolution of the images, we are compressing all these images into the 64 by 64, while also changing the dimension of the pixel from the 3 to 4. So which means that we are taking the RGB images into the 512 by the 512 images as input. And we basically train the autoencoder in terms of the latent here becomes another the 2D image, but it's kind of some sort of the feature image, some kind of 4-channel image. We don't know the meaning of each of the channel, but just like having the 4 channels while decreasing the resolution from the 512 by 512 into the 64 by 64. So the whole idea is that we first train this onto encoder in terms of compressing all the data. So we are basically having some pre-trained encoder of the decoder and the images. And then the noise prediction, the network is basically trained in the latent space of that specific autoencoder. And typically in the early models, like people just use the UNet architecture for this kind of the noise prediction. And we also want to discuss some kind of the later the models, which is not using the UNet, but the transformers. But also basically some kind of the characteristics of like this kind of the model is that we are having the bunch of some kind of the attention the models. So if you have learned about the attention models, it's basically utilizing that specific idea here. And also the way that we are incorporating some kind of the extra condition for the CFG is basically also having some kind of the extra encoder for each of the input. So for the text input, we can have some kind of text encoder, or some image input, it can be some another the image encoder, whatever kind of the encoder for each specific type of the conditioning. And then we are basically feeding this information into the cross attention module. So the way that we are basically feeding the extra information is that when you have this kind of the cross attention module, we are computing the query value as kind of the output of the UNet layer in the noise prediction network. And then we are calculating the key and the value as the output of the input condition, the encoder. So that's the very typical the idea in terms of like the combining the information of the noise image, which is basically fed into the input to the noise prediction network, and also some extra the conditioning information. And you will see that actually this attention module, which is basically having the self-attention and also the cross-attention as well, the attention modules in this kind of the noise prediction network has some kind of the very interesting some kind of characteristics that can be used in the many applications. So what actually we are going to discuss in our guest lecture, which will be happening next Thursday, is that our guest lecture will discuss some kind of the very interesting ideas in terms of like utilizing this kind of the attention layers in the UNet in a way that we can basically do some kind of the loss of the image anything or some kind of conditional generations. So those are kind of things. And we are not going to get into some more details about all these kind of architectures, but of course, like it might be better for you to basically try yourself to run the code and also see the details of the code. So there are also tons of kind of the library and many kind of some public code implementing this kind of the latent diffusion idea. One of the famous libraries will be this like diffusers. We are also going to use this library diffusers in our assignment 3. So I also recommend you to start to play with this library, diffusers, and see making some many interesting images using that. Any questions? Are JPEG images not only decompressed highly? So the difference with the JPEG is that JPEG, I mean, you can consider using the JPEG, but here basically the idea is that we are decreasing the dimension of the data into some kind of the specific, the lower dimensional kind of things. So actually the key is to decrease the resolution, not just basically decreasing the quality kind of things. So in terms of that, actually, we can consider using the autoencoder that can effectively decrease the dimension. Yeah. Any other questions? But this is also basically very practical the idea in terms of that if you also play with some kind of the high dimensional data for your course project, if you feel that the data that you are dealing with is basically having some high dimensional kind of things, then you can consider basically decreasing the dimension first by training some kind of autoencoder and then running the diffusion models in the latent space. So just like very practical the idea. So using the latent diffusion, now we can get some really high quality results in terms of decreasing the FID. So without the latent diffusion, still we could get like 4.59 kind of things. And after using the latent diffusion, we can further decrease the FID. Any questions on this? So speaking to the FID, we also discussed like what's the meaning of the FID. Like what we have done in the assignment 1 and 2 were all about basically computing the FID, right? So FID is basically some kind of the most famous kind of the way to basically measure the quality of the generated images. So that is being used in the older cases in terms of evaluating some new image generated models. But we can also see that this is not the kind of the perfect metric in many kind of aspects. But if we quickly see the meaning of the FID, actually to understand the FID, we first need to discuss the Burst-Stained distance, which is also known as the Frechet distance or the Earth movers distance. So that's why we are basically having the Frechet inception distance. Actually, the definition is not exactly perfect the same, but people are interchanging the terms in this way. So the meaning of the P Burst-Stained distance is that given that we are having the two marginal distribution, the mu and the nu here, we are basically finding a kind of a joint distribution combining these two in a way that we are minimizing the expected value of the distances, like moving one point to the other. Either we are using some kind of some P norm here for the distance. So it might be a little bit like challenging to understand like what this means. So if we want to clearly understand like the meaning of like this, we can see some kind of some discrete setup. So in the discrete setup, let's think about that we are having this kind of the 1D kind of distribution with some kind of the specific bins here. So let's say this is kind of some sort of it can be like some probability distribution or any kind of the distribution of the mass over the one-dimensional space with some kind of the bins here. And what we want to do is that we want to basically measure the difference between this distribution and the other distribution here in terms of like how much we need to move some kind of the mass from the space to the other kind of the point. So let's say like we are basically, let me do something here. Yeah. So let's say we are basically making some changes from the first distribution to make it to be the same with the second distribution in a way that we are moving things. Like let's say we are moving this to here and also moving this to here. And also we move this blue part into here. So we are basically moving this kind of some kind of the dust or some kind of the mass in each of the bin into some other the closed bin in terms of that the first one becomes the same with the second distribution. Let me clean up these things. So here the question is that what's the kind of the minimum cost in terms of like moving the dust in a way that we can match the first distribution into the second distribution. So the cost of like the transformation is actually calculated as the sum of the mass that we are moving for each of the bin multiplied by the distance of the bins. So as you basically move the dust further into the very far bins, that is like taking more cost, right? So we are basically defining the cost in terms like the mass multiplied the distance and summing or like all these kind of cost and see what's the kind of the optimal way in terms like moving all this kind of the mass to the other points in terms like matching these two. So if we find this kind of like optimal way to basically match this kind of the two distribution, then the cost for that becomes basically the distance, measuring the distance between the two distributions. And here the point is that we can do the same thing, not only for this kind of some discrete distribution, but also for some kind of the continuous distribution that is basically defined as the probability distributions. So that's the basic idea. There are actually tons of many other things that we can discuss here. But here basically the one kind of thing is that if we have like the two distributions as the normal distributions, which are defined with the mean and the variance here, and the two Burst-Stained distance, taking the P as the 2 here, is basically defined into this specific form, which is basically very easy to calculate. So what we can see is like, it's kind of a summary here is that, given this kind of two normal distributions, we can easily compute the Burst-Stained distance between these two into this formulation. So that's the basic idea. So what we are doing in terms of defining the Frechet inception distance is that we are measuring the Frechet distance, the two Burst-Stained distance between the distribution of the real images and the distributions of the generated images. And then how we define the distribution is that we are basically putting all those images into some kind of the latent space. Specifically, we are using the latent space of the inception V3 network, which is basically famous the network for the classification, which was introduced in 2015. And then basically mapping all the images into the latent space of like this specific network, and basically modeling all the distributions, each of the distribution as the normal distribution, and calculating this formulation. So this is basically like one way that we can measure the difference between the distributions of the like real images and the distributions of the fake images. Is it clear? Yeah, then there will be lots of the questions in terms like why we are using the inception V3 network, like why just don't you use some other network for that? And why do we also model all the distributions as the normal distributions, while the distributions will be more complex, way more complex than the normal distributions, right? So you can say that actually this measure is not that kind of the perfect measure for the basically metric in terms of the measuring the quality of the generations. There's lots of issues. Obviously, like it doesn't make sense that we are modeling all these like distributions as the normal distributions. And also here, the one big question might be is that like would be good to really use the latent space of the inception V3 network. Basically, what we also expect to see is that if we have some kind of the similar images that look similar into like human eyes, these images should be mapped to some similar points in the latent space, right? So the similarity in terms of the perception of the images should be basically the same into some kind of some distance matrix in the new space. Here, the question is that, is it really true? Actually, there are lots of the research which is showing some kind of the problems of the FID. Like one of the research that has been introduced in the like 2022 is that, so what they played here is like we are having some kind of a set of the images, and then just like compressing all these images using the JPEG format, like having the like 75% of like preserving the images. Then you can see that like the leftmost image is the raw input images, the input image, and the rightmost image, the compressed image using the JPEG. And can you tell the difference between this and this? Yeah, I cannot personally tell any difference between these two. So from the human perception, I think there's no difference between this and this image. But what happens is that if we basically map all the raw images and also the like JPEG compressed images into the inception, the latent space, and measure the FID, then you can see that the FID becomes like 20. So the FID that we have seen in the case of like the latent diffusion was like 4 or 5, right? But now it becomes like 20, which means that the latent space of the inception network may not be the best place to capture the similarity across images. Like one example showing some kind of the problem of the FID. Any questions on this? Yeah, so here the one question in the Zoom chat is that in the stable diffusion, they are not using the autoencoder, but using the variation autoencoder for the compression. Yeah, that's true. Actually, I basically skipped this kind of like detail. But the thing is that actually they are using some kind of the, not the autoencoder, but having the KLD divergence term in terms of like regularizing the distributions of the latent variables in the latent space. So the good thing of the variation of the autoencoder is that it's not basically just like autoencoding all the data, but also basically enforcing that all the latent variables in the latent space to be basically follow some kind of the prior distribution, which is the the standard, the normal distribution. So in terms of that, we can basically better basically compress all the data in terms of like having all the latent images to be distributed following the Gaussian distribution. That basically makes the training of the noise prediction to be more like stable. So that's the kind of like the idea that we can think of as kind of some sort of the data the augmentation or like data the normalization. So basically, when you normalize all the input data in the neural net training, we can typically get some kind of the better result. So the way that we are normalizing the input data into the noise prediction network is to regularize the latent variables when we basically train the autoencoder. So that's the reason like why we are using the variation autoencoder instead of the typical autoencoder, having some kind of regularization in terms of that all the latent variables to be distributed following the unique Gaussian distribution. So there are also basically some kind of the trade-off in terms of the accuracy of the reconstruction and also the regularization. So as we basically enforce more in terms of like regularizing more in terms of like for the latent variables, we're gonna lose some kind of the accuracy in the autoencoding the reconstruction. So which means that we need to play well in terms of like having some kind of the right parameters for that K divergence term in terms of like not losing the accuracy that much in the reconstruction in the autoencoding. Any other questions on that? Really? So these are basically the basic idea about basically making some latent diffusion and measuring FID. So now we're also going to discuss some of the ideas in terms like how we can play with this kind of some pre-trained diffusion model. So what actually we are going to do in the assignment 3 is basically using the model which is called the stable diffusion, which is trained with the billions of images. Now, how can you use these kind of like pre-trained models for many other cases? Let's see, like for example, like think about some kind of the conditional degeneration case, which can be basically implemented with CFG. But here the question is that, as I said, like the typical the unconditional model is trained with the billions with the images. And here the question is that if we want to make some kind of the conditional model, should we also have another the billions of the pairs of the images? So these are some examples that we are generating images from some sketches or some kind of edge images or some kind of some pose map like this. So there are many other kind of examples, like making some images from the depth images or some normal map. So we're gonna also get into that. For all those kind of some conditional degeneration cases, if we need to basically collect like billions of the pairs of that will take lots of the cost, right? And for most of the cases, even it won't be possible to collect billions of such kind of the pairs to make a single diffusion model. But the thing is that while we do not have the billions of the pairs of the input and the output, we have the billions of the output, some kind of the realistic images. So here the basic idea is that can we somehow convert a pre-trained the diffusion model, which is trained with the billions images, into some kind of the image conditioned model, while just having relatively way smaller the size of the input output the pairs, for example, like 100,000. So let's say like we have the diffusion model trained with the 5 billion images, and we are having the 100,000 pairs, the input and the outputs, like the sketch to the image and or the pose to the human body images. Then how can you convert the unconditional diffusion model effectively into a conditional model? So that's the idea of the ControlNet. This is specifically the case like when both the input and the output are basically images. That can be applied to the 3D and many other kind of cases. But basically, this is the case like when the input and the outputs are basically having the same form, specifically images in this case. So this is like very practical, the idea. There's no theory here. It's like all about basically how we're going to implement those kind of things. And here the basic idea is that we are basically using some kind of a fine-tuning approach. So let's say like we are not training the neural network, the noise prediction network from scratch, but we start from the pre-trained the noise prediction network. And then we fine-tune, like further training this diffusion model using some kind of the relatively like a few images. But also the thing is that we are not changing the neural net parameters. There will be lots of the layers with some kind of the parameters. We are not changing them, but we are introducing some kind of the additional, some kind of the learnable parameters, like additional layers into the network. And then we only tune those kind of some extra parameters. So that's the idea about the fine-tuning the approaches, and that are basically used in the many tons of the applications. So specifically for the ControlNet, let's see the kind of the architecture of the network without any kind of details. Like what we are going to see is that, so the left-hand part here is basically the union architecture that we have seen in the previous slide. And what we want to do is that we are taking the extra input, which is the condition image, right? And we need to somehow process the condition input, right? So in terms of processing the condition image, we are fully reversing basically the parameters of the pre-trained neural network to process the extra condition here. So here the question is that how we can basically fully reverse the information in the pre-trained network to process the extra input here. So here the question is that what's the input to the original noise prediction network? What was the input to the original the noise prediction network? Let's briefly just recap. What is the input and the output for the everyone is wrong here. So basically the input to the neural network is the XT, which is the latent image, which is also the noisy image. And the output is the noise, epsilon t, right? So input is the latent image, the noise image, and the output is basically the noise. And in the latent diffusion case, everything basically works in the latent space. So input also becomes the noise image in the latent space, and also the output becomes the noise in that latent space, right? So in the formulation of the DDPM, DDIM, the input to the neural net was basically XT, and also the time t, right? Do you remember that the epsilon this theta was taking the xt as the input, which is the noisy image, the latent space, and also the time t here. And as the output, we are basically getting the epsilon t, which was basically the noise in the noise prediction, right? So basically, we are having this kind of the architecture, which is taking the noise image in the latent space as kind of the input here. And we want to basically fully utilize this information to process the extra input, which is another the image, but not the noise image, but it's the conditioning image here, right? So what we do is that, let's say like we are not gonna touch any parts of the existing the neural network, any parameters of the existing neural network. So the full network is frozen. So we are not touching this. But we are going to like copy the half of this, the encoding part of the neural network to process the additional, the conditional image here. Okay. So it's not just like copying the architecture, but we also copy all the neural net parameters in terms of that it can immediately basically start to basically process any input data here. And the output of the encoding here is basically somehow like combined into the layers, the decoding part, with some kind of the model which is called the zero convolution. So this is the basic idea. So what is the zero convolution here basically means? Zero convolution is basically nothing but basically having only the two parameters, like any kind of the input here, so which is typically the image, some kind of the into some resolution. We are having some kind of the two like the parameters, like one is the scaling factor, and the other one is basically some kind of the some offset. So for every single pixel, we are basically scaling and also adding the offset using these kind of like shared parameters, the A and B. So you can see that like this like single module is like very light module having just two parameters like A and B. And we are basically having this kind of like bunch of the zero convolution the layers into some of the parts. And also while we are basically copying the neural net parameters here from the network, the pre-trained network, we basically allow to basically modify the numbers here, modify the parameters of neural net here, while basically freezing the parameters in this part. So you can see that the only kind of the parameters that we are tuning is on the right-hand side. So the half of the parameters here is basically kind of, this is the biggest part, which is that we are copying from the original network, while basically we are having some very few parameters for the zero convolution here. Just two numbers, A and B. See? And let's see basically how we are basically connecting this kind of the network. So we can basically, for let's say, for each of the case here, like for each of the intermediate layers here, we can simplify like all this kind of architecture into this form. So this is basically the neural network that we have as kind of like pre-trained kind of part. So we are not gonna basically touch this part here. And then we are copying exactly the same network here, also with their kind of the parameters as well. And then we are having basically zero convolution before this part and also after this part. See? So check this out. From the input, the condition C here, we are having the zero convolution here, this part, which corresponds to this like first zero convolution. And then this output is like added to the X here, fed into the same network, the copied neural network, which becomes like this whole part. And this whole part is also fed into the zero convolution, making like this whole part. And then the output is now as kind of offset to the original neural network. So check this out. We are basically copying the neural network here while basically having the two zero convolution neural network. See? So here the only key idea is that the way that we are basically fully utilizing the pre-trained neural network here in the trainable the copy is that at the very beginning, it becomes the same, that we are not having any condition. So what we want to do is that we want to gradually basically fine-tune this kind of the encoding part in terms of that it can basically incorporate starting from basically the original input X here, and it's slowly like switching to incorporating not only X but also C as well. So the goal is that at the very beginning, we make the neural network to basically just process the X as the input. Then we know that this like the network will perform well with this the same the input X here, because like this network was trained to basically take the noise image data to XT here, not the conditional image. And also in this part, in terms like the adding the output over here, it's the same. We want to start the fine tuning in terms of that it becomes the same, not having this condition, but just directly feeding the output of like this original network. And then we are gradually basically mixing the output from this kind of the additional parts in terms of that we can basically fine tune the neural network starting from the original input basically blending some kind of the new input condition. So in detail, what this basically means is that let's see, so let's say this is the conditional image and this is the noise image input here, right? And the role of the first zero convolution is that I mentioned that this zero convolution, these like two parameters and the A, B are basically initialized into the zero. So let's say like this like A and B are basically zero. Then what does this mean is that at the very beginning, there is no effect of the C here. So the output of the zero convolution will become zero. See? Because like this A and B are basically zero, right? This means that at the very beginning, it will be the same, that we are directly just feeding this X into this network, right? And this network was trained to basically take this X, the noise input, as noise image as the input, right? So it knows like how to basically take this as kind of input. But as we basically fine tune the neural network, we're gonna slightly adjust this A1 and B1 in terms of that the output of the zero convolution becomes not zero, but something coming from the conditioning. And then we're gonna slowly basically fine tune the encoding part in terms of that now we can incorporate not only the X here, but something that is basically given from the condition, from the zero convolution, right? So that's the basic idea in terms of that we are slowly basically blending the information coming from the conditioning in terms of that while we are starting from the case that we are not taking any information from the condition. Make sense? So again, like we are starting this training in terms of at the very beginning, we are not taking any information from the condition because like the output of the zero convolution will become zero. And just like directly taking the X as the input. But over training, this A1 and the B1 will be adjusted in terms of that now we are slowly feeding some of the information from the condition here into this kind of encoding part. Make sense? And it's also the same in terms of when we blend the information of the output of this like extra branch into the original branch. So also in this case, we are having the zero conversion again here, which means that at the very beginning, the whole output of like this extra branch will become zero because like this A2 and B2, these parameters are initialized into the zero. So at the very beginning, there is no effect of this kind of additional the branch. We're gonna get the results that we are directly feeding the X as the input and just like taking the output of like this original network. But over the training, if we also slowly like adjust these two parameters, there will be some kind of effect of like having this kind of the new branch, having some kind of information coming from this zero conversion to the original branch, adding some kind of offset here, in terms of that the network is basically fine-tuned properly to basically blend these kind of two outputs. So that's the whole idea of like having the zero convolution. Basically, we are having the very small number of the parameters that is basically initialized from zero in terms of that at the very beginning, it becomes the same with basically not taking any kind of the condition, but basically slowly taking some information from the conditioning with basically these two small parameters and also the parameters copied from the original network in terms that we can slowly basically fine tune this kind of the extra encoder for the condition. So this is basically very practical idea in terms of like implementation. So in a way that we can basically incorporate some kind of the new condition. And basically the good thing is that this idea can be basically used for any kind of the image condition. So as you can see, these are all different types of the conditioning, like the sketches and the normal maps and the depth map, and also the edge maps and also kind of layout, many kind of things. For all the different types of the images, we can basically use these kind of the ideas. And also we can fine tune the branch with some relatively like very small number of images, using only the 100,000 images without having the 5 billions, we can still get some very good quality of the images. So let me briefly basically share like what we can get with the idea of the ControlNet. Let me switch to my screen. So this is basically the GitHub repository, the ControlNet, the original, the inventor. So you can, I recommend you to really just play with this. And also the assignment 3 will be basically just like, just working on this kind of code. So these are some of the examples that we are taking this sketch or some edge map as the input and making some aligned images with some kind of variations. And more sketches and this kind of some more like some sort of the drawing things, making some of the realistic images. And it can be really some kind of the some doodling, some raw quality the sketches. So you can also get some images. And also for this kind of some human pose information, we can make some kind of the images as well. So these are also some of the examples that we are taking the pose from the input image using some another network like extracting the pose and then making some other kind of the human characters with some kind of the new text description, the astronaut on the moon. And this can be also cases like taking this kind of some layout images or some segmentation map as the input, and also some depth map as well. So I recommend you to basically check out this. So these are very practical the ideas without any kind of theory. So more about some kind of the implementation, some ideas. And these are some kind of the comparisons with the other cases. So if we do not use any kind of like the zero convolution, we get the worst quality. So even when you basically copy the encoding part, but without using the zero convolution, we can also get the results, which is not converging that well. But actually, when you make some kind of the some lighter the architecture with the zero convolution, then we can actually get the even better the quality of the images like this. So this is like the one idea in terms of basically converting some kind of the unconditional diffusion model, especially the image diffusion model into the conditional diffusion models. And there can be also many other ideas. Especially the ControlNet works well when the conditioning images are kind of like aligned with the output that we want to see. But what if we have some kind of the more like weaker some information, like just having some kind of the bounding boxes like this. So bounding boxes are basically not giving some kind of the some detailed information about the outputs. For those kind of cases, we can also consider making some kind of taking another some kind of the fine-tuning approach. Like one of the well-known example is this like collision, which is not using the same idea of the geo-convolution, but also introducing some kind of the extra module, which is called the gated self-attention. It's basically the same in terms of like having some kind of the fine-tuning approach. It's starting from the pre-trained model, freezing all the parameters there, and adding some kind of the extra layers of the modules, and only basically fine-tuning these parameters with some kind of the extra some training the data. So using this kind of the way, it's basically another some kind of fine-tuning approach in terms of that now we can better incorporate with some kind of some other types of the conditioning. And you can actually check out there are actually tons of the ideas doing some kind of fine-tuning in terms of like converting some kind of the unconditional model into the conditional model. Any questions on this? Yeah, so C should be image with the same dimension. Yes. So that's also kind of the some kind of the restrictions of the ControlNet in terms of the conditioning image should be also the same type of the data, which is the image in this case, and also the dimension should be exactly the same because like the idea is that we are utilizing the encoding part of the pre-trained the noise prediction network. So that's a good point. Any other questions? And should C go through the autoencoder before zero convolution? Yes, because if we want to basically match the dimension for the latent diffusion case, like we also need to basically map the C into the same latent space. And is it shared or along the values element-wise? Yeah, so the A and the B are basically shared among all the elements in the images. So that's why we call this kind of like the convolution for each of the elements. So zero convolution is basically called as like having the one-by-one convolution, which is basically nothing but basically using the same scaling and the observed parameters for every single the pixel in the input images. Any other questions on this? So before we end today's lecture, let me just go quickly read about the ideas about the personalization. So this is not about any kind of technical things. You can also see that this is basically nothing but just like having some kind of fine tuning. But basically what we want to do in terms of like the personalization is that, let's say we want to basically personalize our diffusion models in terms of that, let's say like I want to generate the portrait images with all the different text descriptions, but making the portrait images of like myself for all the cases. So then how can we make the pre-trained diffusion model in terms of that it's like personalized into some specific objects. So here the object becomes like me or something else. Or I also want to make some kind of the images of the same backpack that I have. So then how can you also make the diffusion model to basically understand like what's basically my backpack, and basically making the backpack for all the different kind of the descriptions. So for those kind of things, we can also consider using the fine-tuning the approach, which means that given the unconditional, given some kind of a pre-trained diffusion model, we are fine-tuning it while basically freezing all the kind of the parameters in the given neural network, while basically making some kind of the extra difference. So it's basically the same idea of the ControlNet, but the only difference is that now we are not taking some kind of the additional input. For the same input, we are basically making some kind of the extra difference here, which is also kind of running in parallel with each of the layer in the pre-trained the network. So we can really think about basically copying each of the layer while phrasing this, just like only fine-tuning this part. But then the problem is that we're gonna basically double the number of the parameters, right? So that's not what we want to do. We want to basically minimize the number of the new parameters in terms of that we can convert it way faster from the new small set of the images. So in terms of like decreasing the number of the parameters, actually what we can do is that, so let's say like we are having some kind of a single NLP layer here, right? With some kind of the D-dimensional input and also the D-dimensional output. Then like one single D MLP layer actually can be considered as basically having some kind of a linear function, like multiplying this like D by D matrix, plus some kind of like applying some kind of activation function here, right? So which means that we are having the D by D parameters in this specific D linear D layer. And we want to basically decrease the number of the parameters while basically approximating this matrix as much as possible. So in terms of that, like what we are doing is that we are basically like approximating this like D by D matrix as kind of the multiplication of the two like very thin D matrices, which are basically the low rank D matrices. So instead of like having the D by D matrix, now we are multiplying like D by R matrix multiplied by the R by D, while this R is basically way smaller than D. So we can think of like this is kind of like some approximation of this kind of the very big matrix into the very two thin matrices. And this kind of the matrix demultiplication can be considered as kind of actually having the two linear layers, while basically having some very low dimensional, some kind of the intermediate, the latent the variables here. So instead of like having the like one single the giant the linear the layer here, we are basically introducing like two small the linear layers while having the bottleneck in the intermediate the latent the variables. So this is basically the idea in terms of actually decreasing the number of the parameters while basically making this kind of some additional the parallel branch. So basically by having this kind of the two layers, we can basically fine-tune, basically introduce some kind of a few number of some kind of the new parameters, and then fine-tune this network in terms of that it basically now overfitted into some specific object or specific types of the images. So if I also show some of the examples for this, so the thing is that this idea of basically having fine-tuning the network for some specific style of the images or some specific objective of the images is very common. So even now, this is the website, which is the market of this kind of fine-tuned models. So you can basically buy some kind of some diffusion models, some fine-tuned diffusion models, which are basically fine-tuned into some specific style. So for example, I think so we can have some kind of some fine-tuned models, basically for some kind of the CAD drawings here, or I don't know, some animation images like this, or some kind of some animation images again here, or some kind of the neon sign images like this. So those are all the cases that people basically fine-tuned some existing, typically the stable diffusion into some kind of the images in some specific style or having some kind of the specific objects. And you can easily download those kind of some fine-tuned models in terms of that you can basically generate some kind of images in some specific styles. So these can be basically used to generate some kind of webtoons or make some other kind of things. So this is, you can see that this is really basically a very common idea in terms of like doing some kind of a personalization for some pre-trained diffusion models. So let me stop here. We are also having some more slides about some kind of GeoShot applications, but maybe I can continue those things in the next lecture. So as I said, like we are not going to have the lecture on this like coming Wednesday, but we're going to have the session for the assignment 3 next Monday at the same time. So please also join the offline session as well. And then after that, we're going to have the guest lecture next Thursday at the 4 p.m. And we're going to also continue the other applications in the week after next week. And if you have any questions on this, please feel free to leave the questions in the Slack workspace. Okay. So I will see you next Monday. Okay. Thank you. Bye.